A scalar is a physical quantity that has a magnitude but no direction. For example, when you say, I ran 5 kilometers, or the temperature is 30 degrees Celsius, you're describing scalar quantities. It's the number or value that matters here, not the direction. Some common scalar quantities include distance, speed, mass, temperature, and time. Unlike scalars, vectors have both magnitude and direction. This means we're not just interested in how much of something we have, but also where it's going. A great example of a vector is displacement. If you say you ran 5 kilometers, we know the distance, but not where you ended up. Depending on the direction, you could have reached the bank, the store, the park, or even home. But if you specify that you ran 5 kilometers east, we now know you ended up at the store. This is a vector quantity because it gives us both the distance and the direction, and it's called displacement. Other common vector quantities include velocity, acceleration, and force. Vectors are represented by arrows, where the length of the arrow shows the magnitude, and the direction of the arrow shows, well, the direction. Now, let's explore how we can add vectors together to find a resultant vector. There are different scenarios depending on the angles between the vectors. We'll look at 3 common cases: vectors in a straight line, vectors at a right angle, and vectors at other angles. Next, let's look at 2 vectors that are in a straight line. If 2 vectors act on a point in a straight line, the resultant vector can be found through a graphical method and calculation. If both vectors point in the same direction, you simply add their magnitudes to get the resultant. For example, if vector A is 5 units and vector B is 3 units, both pointing east, the resultant vector C is 8 units east. However, if the vectors point in opposite directions, you subtract their magnitudes. Suppose vector A is 5 units east and vector B is 3 units west, then the resultant vector C is 2 units east. Now let's move on to finding the resultant vector when 2 vectors are at a right angle to each other. Imagine 2 vectors, one pointing east and the other pointing north. Graphically, we can represent them as arrows forming a right angle, like the sides of a right-angled triangle. In this scenario, we can use the Pythagorean theorem to calculate the magnitude of the resultant vector. The Pythagorean theorem tells us that the square of the hypotenuse, the longest side of a right triangle, is equal to the sum of the squares of the other 2 sides. Let's say a plane flies 30 kilometers east and then 40 kilometers north. To find the plane's total displacement, we apply the Pythagorean theorem. We calculate the square of each vector. C squared equals 30 kilometers squared plus 40 kilometers squared. This equals 2,500 kilometers squared. Now remember, this is the value for c squared. So to find the magnitude of the resultant vector, c, we take the square root of both sides. The square root of 2,500 square kilometers is 50 kilometers. This means the plane's displacement, or the resultant vector, is 50 kilometers. Now that we've calculated the magnitude of the resultant vector, let's figure out its direction. To do this, we use trigonometry. In a right-angled triangle, we have 3 sides: the opposite side, the adjacent side, and the hypotenuse. The opposite side is the side opposite the angle we're trying to find. The adjacent side is the side next to the angle. The hypotenuse is the resultant vector, which is the longest side. To find the angle, we use one of the 3 primary trigonometric functions: sine, cosine, or tangent. But how do we know which one to use? It depends on which sides of the triangle we're working with. Sine is used when you know the opposite side and the hypotenuse. Cosine is used when you know the adjacent side and the hypotenuse. Tangent is used when you know the opposite side and the adjacent side. Since we know the opposite side, 40 kilometers, and the adjacent side, 30 kilometers, we'll use the tangent function. The formula for tangent is tan theta equals opposite over adjacent. So for this example, tan theta equals 40 kilometers over 30 kilometers, which equals 4 over 3. Now, to find the angle, we take the inverse tangent of this ratio. Using a calculator, we find that the angle is 53.13 degrees. This tells us that the plane's displacement is at an angle of 53.13 degrees north of east. We can also express the direction of the plane's displacement in terms of bearing, which is the angle measured clockwise from north. Since we calculated an angle of 53.13 degrees north of east, we subtract this from 90 degrees to get a bearing of 36.87 degrees. So, the plane's total displacement is 50 kilometers on a bearing of 36.87 degrees. When two vectors are acting at a point but not at right angles, we can determine the resultant vector using a graphical method. This involves drawing the vectors to scale and measuring the resultant vector's length and bearing. Let's work through an example to see how it's done. Two forces act on an object, one of 6 Newton on a bearing of 30 degrees and another of 4 Newton on a bearing of 180 degrees. The first thing we need to do is choose a scale to represent our forces. Since we have 6 Newton and 4 Newton forces, we'll use a scale of 1 centimeter equals 1 Newton. This means we'll draw the first vector as 6 centimeters long and the second as 4 centimeters long. Now, from a common starting point, we'll draw the first vector. This is a 6 Newton force at a bearing of 30 degrees, or 30 degrees east of north. Next, we'll draw the second vector, which is 4 Newton at a bearing of 180 degrees. This one is easy. It points straight down because it's due south. We'll measure and draw a 4 centimeters long line downwards. To find the resultant, we will use the parallelogram method. We'll draw lines parallel to both vectors. From the head of the 4 Newton vector, draw a line that's parallel to the 6 Newton vector, and from the head of the 6 Newton vector, draw a line parallel to the 4 Newton vector. This forms a parallelogram. The diagonal of the parallelogram represents our resultant vector. We'll draw this diagonal, starting at the origin where both vectors began and ending at the opposite corner of the parallelogram. Let's measure the length of this diagonal. In this case, it measures 3.2 centimeters. Now, since we're using a scale of 1 centimeter equals 1 Newton, the magnitude of the resultant force is 3.2 Newton. Lastly, we need to find the direction of our resultant vector. Using a protractor, we measure the angle between the resultant vector and the vertical axis, which represents north. In this case, the angle is approximately 68 degrees. So the resultant force is 3.2 Newton on a bearing of 68 degrees. That's it for today's video. I hope you now have a clear understanding of scalars and vectors and how to determine the resultant vector. If you found this video helpful, make sure to give it a thumbs up, subscribe for more awesome physics videos. Thanks for watching, and see you in the next video.